Hello everybody and welcome. I'd like to start by thanking the organisers for this opportunity to speak in virtual São Carlos. Today I'd like to talk to you about my joint work with Peter Giblin and Ricardo Uribe Vargas on contact of surfaces with circles and their Euclidean invariants. So our story today actually begins with the works of Leonhard Euler and Jean-Baptiste Mernier in the 18th century. Now these theorems both relate the principal curvatures to the curvature of a plane curve you get when you slice your surface with a plane. And then Euler's formula tells you the curvature of any plane section containing the normal line to the surface in terms of the angle theta from one of the principal directions.
Our second theorem is that of Jean-Baptiste Mernier, which extends Euler's theorem to consider arbitrary plane sections, not just normal sections. So if kappa theta is a curvature of the plane cut out in the normal plane, then kappa theta psi is the curvature of the plane curve in the plane cut out by the normal plane that's rotated by an angle psi. So if this at the bottom of this circle is the point on the surface, then this is the normal direction to the surface, and then according to Euler's formula, will give us the curvature kappa theta. So 1 over kappa theta gives you the radius of the osculating circle. And if you imagine a sphere of the same radius, then when you rotate your tangent plane by an angle psi from the normal, then the radius of your new radius of 1 over curvature will lie on this sphere. And this is what Mernier's theorem says. So although Mernier is less famous than Euler, he's also famous for creating the ellipsoid and also for inventing Mernier's dirigible. Now fast forward a few years. Now Ian Porteous was able to extend the work of Mernier. So where Mernier was able to find the curvature of arbitrary sections, in other words, find a circle, the radius of a circle that has osculating 3-point contact with the surface, Ian asked, for which planes can you intersect the surface and obtain a higher degree of circularity? In other words, which can you have a plane section where a circle has 4-point contact with the surface? In other words, it cuts out a vertex on the surface. And he managed to find the following. So if you fix a tangent line to the surface and you look at planes passing through that tangent line, generally, as long as your tangent line isn't a principal line, then you will get one plane for which there exists a vertex. If you take your tangent line to the surface to be a principal direction on the surface, then there will either be no such plane or every plane that has a vertex. And the condition that every plane has a vertex is that the point on the surface is what he calls an ordinary ridge. And then he asks, for which of these planes do you get a higher vertex or circle with 5-point contact? And this is determined by a quadratic equation. So you either get 0, 2, or 1 repeated solution. And the conditions for these is that you get 0 if it's what he calls a sterile ridge, 2, fertile ridge, and 1, a ridge turning point. At an umbilic point, the principal directions are the same as the root directions of the principal cubic. And so you either have 1 or 3 root directions depending if your umbilic is a hyperbolic umbilic or elliptic umbilic. And then each of these principal directions will give you one of these higher order vertices. And then as you approach the umbilic point along one of these directions, the circle shrinks to a point and curls up and dies, as he calls it, which means that the radius of the circle shrinks to 0. How I fondly remember Ian, here he is teaching some children, and here is of course one of his excellent books.
So our current research focuses on the particular case where there is a circle with 5-point contact that lies in the tangent plane to the surface. So whereas Mernier took the normal plane section and then rotated it by an angle psi, he insisted that this psi was less than pi. So in other words, the tangent plane case was excluded. And this is exactly the one that we're looking at. So we introduce the following definition of the vertex curve. So for a smooth surface in R3, the vertex curve, or V-curve, on the surface is the closure of the set of points in the hyperbolic region of the surface for which there exists a circle lying in the tangent plane that has at least 5-point contact with the surface. So the reason we insist that the point of the surface be hyperbolic is that when you intersect your surface of a tangent plane, you get a transverse crossing. Whereas if it was elliptic, you'd get a single point. Now, the vertex curve is a set of points for which there exists a circle with 5-point contact lying in this tangent plane. In other words, it has 5-point contact with the curve at this point, and this happens before you get 4-point contact from one branch, and then the other branch giving the additional point of contact. So we ask for a vertex on one of the branches, hence the name vertex curve. So clearly this is related to the work of Euler, Mernier, Porteus, and his successors. Our original motivation actually came from a different place. So in 2006, André Diatta and Peter Giblin looked at the vertices and inflections that appear in families of parallel plane sections of surfaces in R3. So you take some surface, like here a torus, and for a given point, you consider the tangent plane, and then you move the tangent plane parallel to itself, and you take slices of the surface, and this gives you a curve in the relevant plane. And then you can consider the evolute of the curve, or indeed symmetry sets, and the vertices will correspond to cusps on your evolute. So of course, where you look at the point itself, the intersection with the tangent plane will be singular, either as an isolated point if your surface is elliptic, or a transverse crossing if it's hyperbolic. So in the hyperbolic region, the following three scenarios can happen generically. Of course, when you intersect with a tangent plane, you get a singular transverse crossing, but when you move your plane parallel to the tangent plane in either direction, then we get two smooth curves which exchange branches at the tangent plane. So the circles represent the vertices, either as maximum or minimum of curvature, and in this scenario the number of vertices is 2 plus 2 on either side, so you have 2 on this branch and 2 on this branch, and this remains the same under the bifurcation. In this scenario we go from 1 vertex on each branch to 3 vertices on each branch. And now the vertex curve that we're considering is a Euclidean invariant which separates the regions H1 I from the regions H1 II. So we study this vertex curve using a contact function or a contact map that measures the contact between the surface and the circle lying in its tangent plane. And following from Montaldi, there are two approaches. Either we parameterize the circle and substitute this into the equation for the surface, or we parameterize the surface and substitute this into the equation for the circle. The circle, being of course one-dimensional in free space, is given by two equations, whereas the surface, being two-dimensional, is given by just one equation. So these two approaches yield either, when we parameterize the circle, we get a contact function from R to R. In the second case, when we parameterize the surface, we end up with a contact map from R2 to R2. Now both these approaches have their advantages and their disadvantages. But note, however, we cannot apply Montaldi's theorem, which says that two approaches are equivalent, since in our case, the intersection with the surface and its tangent plane is not an immersion. Points that are of particular interest in the study of vertex curves are hyperbolic cusps of Gauss. Now, these are special points on the parabolic curve which have a free contact with their tangent plane. Now recall, the parabolic curve divides the surface into the elliptic and the hyperbolic region. Recall also that the vertex curve lives only in the hyperbolic region, where you have a transverse crossing with intersection with its tangent plane. And at the hyperbolic cusp of Gauss, two branches of the vertex curve are tangent to the parabolic curve, and they make 3-point contact with each other. Now in the literature there are various names for cusps of Gauss, including godrons, as favoured by René Thom. They are also referred to as ruffles by Coenderink, point de plissement, or plat points, by Korteweg, or tachnodal points of Cayley as favoured by Willard Gibbs. We also investigate the behaviour of the vertex curve in the vicinity of special points on the surface. For example, in a one-parameter family of surfaces, it can happen that two cusps of Gauss come together and annihilate each other. And this we call an A for E contact transition, where here the A for E refers to the contact with the surface and the tangent plane at the point. Now on these diagrams, the thin black curve represents the parabolic curve. In both cases, the parabolic curve undergoes a Morse transition. In the first, we have a hyperbolic Morse transition, or a crossing, and in the second example, we have an elliptic Morse transition, or where the parabolic curve shrinks to a point and disappears. Now, the thick black curve refers to the flecknodal curve, which is a related idea to the vertex curve. This is to do with contact with lines rather than circles. Another interesting point that occurs in one-parameter families of surfaces is that when the tangent plane makes A4 contact with the surface. Here, an elliptic cusp of Gauss and a hyperbolic cusp of Gauss come together to form what's called a double cusp of Gauss, or bigodron. And here, the two branches which have A3 contact then release from each other and go their separate ways. The max and the min here and the directions of the arrows show the rate of increasing radius is associated to the vertex curve. So the final special type of point that occurs generically in a one-parameter family that I'm going to look at today is the flat umbilic. Now this is when we expand the surface in Monge form, the quadratic part vanishes and we can write our function starting with cubic terms. Now the standard way to classify umbilic points of surfaces is to introduce a complex variable and then rewrite the cubic part of the surface in terms of z and a complex number beta. Then the cubic forms can then be represented in the beta plane, or nearly all of the cubic forms. And the classical classification due to Darboux is we have Monstar inside the green deltoid, the white region corresponds to stars, the yellow region called lemon, and the red inside the red deltoid correspond to elliptic umbilics. So I realise now, of course, being in Brazil, I should have coloured the lemons green and the Monstars yellow. As we know, the best caipirinhas are made from green lemons. Now for us, the classification is different, and we have these pictures on the surface, and in the beta plane. These curves, of course, lie in the beta plane. And these correspond to the discriminants of a quintic equation, and it separates the plane into regions 1, 3, and 5, where the numbers correspond to the numbers of branches of the V curve which have 0 radius as a limit as you approach along the vertex curve. You see in each successive picture is zooming in on the propeller shaped picture on the left. You zoom in on the center and then zoom in on the region A here, so you can see the 5 and these thin regions. Okay, so let's look at the pictures of these different types. So it's D4 minus, this is inside the red triangle. This is where we have 3 radius of 0 branches. So you see the red curve, the arrow points in the direction of increasing radius. So as you go along here, one of these red branches, the radius of the associated circle to the vertex curve approaches 0. So there are 3 red branches. Here there is 1 in the D4 plus. This is the 1 branch case. Again, the red branches represent radius 0. And the other cases for D4 plus, here we have 3 red branches with radius 0. And here's the example with 5 branches of the vertex curve. So rather than just restricting ourselves to studying circles lying in the tangent plane to a surface, we now like to extend our study to incorporate those that lie in other planes. Since those in the tangent plane are special, what about if we consider those just in the normal planes? We could then extend this to think about those planes that make a fixed angle to the normal in the surface, just like the angle psi in the work of Mernier. So particular angles, say pi by 4, might be of interest.
Then we'd like to vary, finally we'd like to vary the angle psi and consider all circles passing through the point that give contact with the surface. So let's first look briefly at the normal circles case. For each point on the surface, there will exist one, three, or two coincident directions on the surface for which the normal plane cuts the surface in the vertex. And this is determined solely by the surface's cubic form. And we define these to be, in these cases, to be the cubic elliptic, cubic hyperbolic, or the cubic parabolic when the two directions coincide. And we define this locus of points for which the two coincide, the cubic parabolic curve. And so these directions, either 1 or 3 or 2, these give rise to a natural vector field determined by a binary differential equation in the cubic terms of the surface. Another invariant we define is the normal vertex curve. Now this is the locus of points on the surface for which there exists a normal circle making 5-point contact, or a higher vertex on the intersection of the surface of a normal plane. So this is akin to the vertex curve in the tangent plane. Now this work is related to the work of Fukui, Hasegawa, and Nakagawa on the contact between surfaces and cylinders. So there are many examples of binary quadratic differential equations giving line fields on surfaces. For example, we have principal directions which are related to the contact of spheres. And we have asymptotic directions in the hyperbolic region which is related to the contact with planes. Contact with normal circles naturally gives rise to a cubic differential equation. It's just like in the work of Fukui, Hasegawa, and Nakagawa on the line fields associated with cylinders. So now we wish to extend our search to look for circles lying in planes that make a fixed angle to the normal to the surface. So we write our surface in Monge form, and we consider planes whose normal is as follows. So for a fixed angle phi. So phi here is the latitude of the normal line to the plane, where t is chosen to be in the case where phi is equal to 0, so in the normal plane case, then t measures the angle between the plane and the positive x-axis. And then we ask, for which values of phi and t does there exist a circle that makes 4 or 5 point contact with the surface at a given point? So in other words, does the plane intersection of the surface have a vertex or a higher vertex, respectively? So in the phi t plane, which represents all the possible planes that we can intersect our surface with, we can plot the values of phi and t for which that plane, when intersected with the surface, gives you a vertex in the intersection curve. Now the value phi equals 0, of course also the value phi equals pi, give the normal planes, and the value phi equals pi by 2 corresponds to the tangent plane. And of course these two sides are identified, and this phi t is actually the projective plane. So when looking at this picture, we should identify phi and t with minus phi and t plus or minus pi. So we can show that by taking this top corner flipping it over, and it matches up with this corner down here. And similarly, you could do the same with this corner, appears down here. Now here we see some just numerical examples of surfaces that show some of the important features. For example, if we have an elliptic point at the surface with Gaussian curvature positive, then the tangent plane phi equals pi by 2, you have two branches coming into the origin. Remember, this t equals 0 and t equals pi and minus pi are all identified, as these two are identified as well. And if the cubic pi has 3 roots, then there are 3 branches corresponding to phi equals 0 and phi equals pi when you identify correctly. Now the hyperbolic point on the surface with Gaussian curvature negative, we have 4 branches tending to the origin. For parabolic region, we have at the tangent plane, we end up with one of the branches being tangent to this line, phi equals pi by 2. And if we take the cubic part to have 1 root, then there's just one direction in the normal plane once these two are identified, which give a vertex. And finally, we're looking at a picture of a cusp of Gauss, and here we have a crossing at the origin, and the whole of the phi axis give vertices. Recall how we were able to use a contact map from the plane to the plane in order to study the contact between a surface and a circle lying in its tangent plane. This is where the surface was parameterized and the circle was given by two equations. Well, we were able to extend this idea and consider a more general setting where we study the contact between surfaces and general circles. In this case, the limiting zero radius circles, which lie in the tangent plane, give a contact map of corank 2. If the point in question on the surface is not an umbilic point, then following Mather's notation, the contact map is contact equivalent to the singularity I22. If, on the other hand, the point is an umbilic point on the surface, then the contact map is contact equivalent to the singularity IV3. X squared plus y squared, the first component, and the second one can be reduced by contact equivalence to x cubed. So we only have two singularity types. Now, using this kind of map, Montaldi was able to show that at an umbilic point there are in fact 3 branches on the surface for which there exist circles making 6-point contact with the surface. So you have a point P on the surface. Here is a circle with 6-point contact which lies on the Mernier sphere, and then as you approach the umbilic point x0, this circle will collapse and shrink, and as he calls it, curling up and dying, where this circle falls either on its back and shrinks to 0, or in this case, the other scenario, it shrinks to 0 and falls on its face. And the type you get depends on the type of umbilic point, if the umbilic point is hyperbolic or if it's elliptic. However, the contact map only gives us 2 types, I22 and IV3. So, if we'd like to learn more about these circles, we can consider the map under special equivalences that preserve certain parameters. And this work is related to the work of Viktor Gorinov on projections of complete intersections. So if we take some of Viktor's standard singularity types and look at some versal unfoldings, and then project these to various parameter spaces, we get surfaces which are clearly related to circles of contact. And this is an ongoing area of research. So this singularity relates to when the surface is a hyperbolic point, this one when the surface is elliptic, and this one, for example, when at an umbilic point on the surface. E agradecimentos para sua atenção. E obrigado de novamente aos organizadores. Sorry I couldn't mention everybody in the talk. Notable papers include that of Bill Bruce, line circles, focal and symmetry sets, Maria Carmen Romero Fuster, stereographic projections and geometric singularities, and also Vladimir Zakal-Yukin on singularities of circle surface, contacts and flags. There's also a master's dissertation in Portuguese of interest on Carol Molina Sanchez. Here's some references. E espero vê-lo em 2022. Obrigado.